Hello, everybody. Very nice to see you. What I'm going to talk about is we all teach performance modeling. We've been teaching it for a long time. Everything I say is going to be entirely obvious to you, so nothing is going to be difficult. But what I would like to do is talk about work that I do with companies. And when I do this work with companies, there's certain questions that they ask me over and over and over. And they're very, very basic questions. Nobody's going to have any confusion about these questions, but these are the questions that I get all the time. And so my feeling is by discussing these questions, we can now talk about how we can gear our courses to really make sure that we answer these kinds of questions. I'm teaching my class right now, my class in performance modeling. I teach it out of my book that you see over here. I typically have 50 people, 50 graduate students in the class, and they find it very interesting, but also difficult. So I try to make sure that I at least get the basics in there, and that's what I'm going to talk about. Okay, so when I talk to companies, the number one question that I get is my system utilization is low, my load is low, so why are my job delays so high? I can't tell you how many times I've been asked this question. Every time that I go and consult, it seems that the question is, we have high delays, we don't understand why, we'll show you our utilization numbers, they're really low, what's the problem? And the answer is very simple for performance modelers. The answer comes from Kingman's approximation. So if you think about a first come, first serve queue, and you have these jobs of different sizes, some are big and some are small. And then you think about arrivals coming into the queue, so these are the arrivals. And here S is a random variable denoting the job size. Okay, again, some are big sizes, some are small sizes. And then A is a random variable denoting the inter-arrival time, the time between arrivals. And we all know this famous approximation, which says mean delay is proportional to this quantity. Now, the row here is one piece of it. That's just the utilization, okay? And certainly utilization makes the big difference. But unfortunately, there's two other things that make a difference. So these are the squared coefficient of variation of the size, and this is the squared coefficient of variation of the inter-arrival time. And if this squared coefficient of variation is high, okay, which it typically is, then your mean delay is high even when your utilization is low. So the most recent company I talked to, the utilization was 40%, but the squared coefficient of variation of job sizes was very high. So let's talk about what it looks like, the squared coefficient of variation. So back when I was a PhD student a long time ago, okay, I wrote a paper on Unix jobs and what they look like. And this is a picture of the sizes of the Unix jobs. This was how many CPU hours Unix jobs were using. And this is the tail of the distribution, the probability that the size exceeds X. And you can see on a log-log scale, this is basically a straight line on a log-log scale. And what that tells you is that the job sizes are a bounded Pareto. I say bounded because there's a limit to how big jobs could be at the time. There was an upper limit, but it was a Pareto with alpha of around 1. And as we all know, that's a highly variable distribution, but because it was bounded, the squared coefficient of variation was still finite, okay? So the squared coefficient of variation, this was back in 96, okay, 1996, was 50. 50 is pretty big, right? Because an exponential is 1, okay? So 50 is a pretty big number. Moreover, the top 1% of jobs, the biggest 1%, I found comprised 50% of the load. So it's just 1% of jobs, but they make up 50% of the total load, okay? So they're really big. So I was wondering back in my PhD, you know, this seems like a big problem. We really need to start, you know, having solutions to deal with it. But today's jobs are actually much worse than this. So typical companies that I go to, the squared coefficient of variation is 200, 300, you know, I mean, much bigger numbers. But I really would like to talk about this one study that, that I participated in at Google. And so these are the jobs handled by Google. A lot of these are like big machine learning jobs, all sorts of different kinds of jobs, really big jobs. This is in Eurosys 2020, so it's a very recent paper written by some Googlers and myself. And in this paper, we again looked at the job size distribution. And again, you see it's basically a straight line on a log-log scale, okay? But when you actually try to fit the line, you see that it's a bounded Pareto where alpha now is a lot lower. It's 0.69. And what that means is the squared coefficient of variation is going up. And in fact, the squared coefficient of variation is 23,000. Okay, now you might think this is crazy. I thought this was crazy. I went back, I remeasured everything, I looked at everything, I tried to, I was like, no, the numbers must be wrong, something is wrong. But really, that's how much variability they have going on. This is at the jobs being run at Google. This is millions of jobs. And when you look at the top 1% of jobs, they actually comprise 99% of the load. So the biggest 1% are really, really big. Okay. Now again, it's still finite. Okay, it's not an infinite distribution. There's still a limited amount of time, but there's many orders of magnitude difference between small jobs and big jobs in these distributions. So you can go to look at the paper for more details. In any case, the thing that I want to point out is when you have this very high t squared over here, you're going to have high delay, and then you're going to have to figure out what to do about it. So this brings me to my second question that I get. The second question is, what can I do to lower the delay? And what I'm going to do is I'm going to give you 3 different solutions that I give to companies, and all of them are about lowering the effect of the job size variability. Because it's the fact that the job size variability that's high, that's what's causing our delays. Usually it's not that utilization is high. Everybody knows to keep utilization low. It's the job size variability that's causing the problem. So how can we lower it? So the first solution 1, is to simply schedule to favor the small jobs. You want to take the small jobs and isolate them from the big jobs by moving them ahead, okay? So the typical type of solution is something like shortest remaining processing time. We basically schedule to get the short jobs ahead of the long jobs, so they're not stuck behind the long jobs. Because it's the fact that short jobs get stuck behind long jobs that causes all of the delay. So here, instead of doing first come, first serve, we're going to run things like shortest remaining processing time, where short jobs get to run ahead of long jobs, okay? And you see the jobs are ordered based on size, okay? This says at all times, we're going to pick to run the job with the shortest remaining time, what's left. You can also do this in a multi-server system. So you can say, okay, maybe I have 3 servers, but at all times, I'm going to run the 3 jobs with the shortest remaining times, okay? And this is one way of getting the short jobs to not be stuck behind the big jobs causing the delay, okay? This is one way of handling it. Now, you might wonder, how much does it really matter? Does it really make a difference to put the short jobs ahead of the long jobs? And the answer is it does. So here's the queue where the squared coefficient of variation is 1. And you can see that SRPT and first come, first serve don't look that different. There's still a pretty significant difference, but they don't look that different when you look at mean delay versus load. But when you have a squared coefficient of variation of 100, the difference is much bigger. So these are just simple, I just did simple analysis with first come, first serve versus SRPT. And there's a huge difference once you have high squared coefficient of variation. And again, the reason is that first come, first serve allows short jobs to get stuck behind long jobs, and SRPT does not allow that to happen. So this is one solution to the problem. Okay. Now you might be worried about this solution because you might say, wait a minute, SRPT is not so nice. Maybe it starves the big jobs. Maybe the big jobs don't get to go. But I wrote a paper way back when in very early on in my career in 2001 that shows that that's not really true. So first of all, when load is less than 1, nobody starves. Everybody will run. Okay. Um, but even when load is something like half, and you're only looking at what happens to the big jobs, there's a theorem called the all can win theorem. It's also in my textbook. And what it basically says is the big jobs are not really hurt under SRPT. Okay, they don't do any worse than in a fair policy like processor sharing, even the very biggest jobs, so long as the load is not too high. Okay, so long as your load is not too high, the big jobs are not starving, and people are worrying about this for no reason. So this is one solution. Okay, but maybe you don't like that solution. So another solution I say to companies, and this is a project I'm working on right now with a company, is again reminding them you can always isolate the small jobs from the big jobs. So the idea here is, you have some kind of data center, a lot of servers, and when the jobs come in, you use SITA task assignment, which separates the short jobs from the long jobs. You want to separate the shorts and the longs. So specifically, you have one queue that's for all the short jobs, and then a different queue for all the long jobs. So you put the long jobs in one queue, the short jobs in another, so the short jobs never wait behind long jobs. And remember that for the types of distributions we're dealing with, these short jobs, this is really like 99% of jobs, maybe even more than that, maybe 99.9% of jobs make up half the load, okay? So almost all the jobs are going to the short place. And you might think, well, maybe the longs aren't being used, but the longs are very, very long jobs, okay? So they are using their servers. So this is another way of handling the issue of high variability, is to just split things up. And I'm happy to take more questions on this. Okay, I know this isn't simple, so simple. Okay, there's a third idea. And the third idea is also a very natural idea, and it's called pooling. And for us, this is all very obvious, but it's not for people in industry. So imagine you have a whole bunch of separate queues, and they're each running their jobs. One thing that you can do is to just pool all the queues together. So what I mean by that is I'm now going to have one queue, and I'm going to take all the arrivals from the other queues and put them into one queue. So instead of each being lambda, there's 4 lambda coming in. And I have the 4 servers, but all the arrivals have gone into one queue. It's a very simple idea, right? I mean, everybody's just sharing one queue, okay? And whenever a server is free, it's going to grab from the one queue, okay? Now, the pooled system has the same average utilization as the original system. I haven't done anything, okay? Same average utilization, same arrival rate, same service rate, same utilization. But we all know that the pooled system has much, much lower delay. This is one of the things I teach a lot, okay? Is the pooled system is a way better system, okay? Because your probability of queuing is much better, but especially because the pooling allows short jobs, especially in high variability, to circumvent the long ones, okay? To get around the long ones. This is exactly what happens, like, when you're stuck in a line and somebody big in front of you, is a big in front of you, you're stuck waiting behind that big guy in front of you, right? But if you have many servers in one queue, okay, then that big one is occupying one server. There are other servers that you can go to. It's very nice for you, okay, to be able to go to one of the other servers. So pooling is a fantastic way to really lower your average delay. And it already works with exponential distributions. It gives you the factor 4, but with more highly variable distributions, it's like it can be, infinitely better to have these pooled systems. So these are 3 solutions for how to deal with variability. Okay, I'm moving to my third question. My third question is, many times people are interested in doing scheduling, because they view scheduling as a nice, easy thing to do that doesn't require any infrastructure and moving things around and, buying new machines. So they like the idea of scheduling, but they say, I'm stuck with first come, first serve because there's nothing I can do because I don't know the sizes of the jobs. So many, many companies tell me I have to do first come, first serve because I don't know which jobs are small. So what am I supposed to do? Okay, I can't do things like SRPT. Okay, and this is simply not true. Okay, nobody's stuck with first come, first serve. So let's talk about this. So the situation that we're in is the situation of unknown job size. So you have a queue and you don't know who's short and who's long. You just don't know it. Okay, you can't tell. Okay, so you don't know the job size. All right, but what you do know is the ages of the job. So age is how long a job has run so far. It's not how long it's been in the system. It's how many seconds of CPU the job has received so far. Okay, how much work has been done so far. You also know the job size distribution because you've been watching jobs complete over time. And so you know that maybe they follow some kind of distribution. Maybe that, there's some likelihood of jobs that are short versus medium versus long versus extra long. And you can start drawing a histogram of the actual distribution over time. Okay. But for an individual job, you have no idea how long it's going to run. You just have this distribution and you have the age. And now what can you do? So the simplest thing that you can do, okay, is one that has nothing to do with size. So here I'm going to show you time as a function of load. And this is first come, first serve, which of course doesn't require any knowledge. And this is SRPT, which we can't do because it requires knowing the sizes, okay? But in between these things is processor sharing. So processor sharing is a very, very simple policy. You time share the server. And what it does without knowing anything about size is it allows the short jobs to complete more quickly. So if you have preemption, if you're allowed to preempt and you can do processor sharing, okay, then you don't need to know the size and you're already getting a big benefit. So these curves are just shown for this particular arbitrary distribution, but there are distributions for which the improvement is even bigger. I drew some distribution. Okay. But maybe this isn't good enough for you, processor sharing. Maybe you really want to get closer to SRPT. So can you still get closer without knowing anything about the size? So here's where you can use the age. So the idea is we're going to run a policy called shortest expected remaining processing time, SERPT. And the way that shortest expected remaining processing time works is we're going to try to compute the expected remaining size of a job given only its age. So given that you know the age of a job, you should be able to compute what the expectation is on the remaining size of a job. Okay, the expectation on the remaining side. And so here I have done the computation. I've computed the expected remaining size as a function of age. And what you see is that this is SERPT, and it's so much better than processor sharing. It's very close to SRPT. And in fact, it's very close to the true optimal, which is Git. Okay, so I'm told to start preparing for questions myself. I'm going to do one more question, question 4, and then I will open the floor for questions. I'll skip question 5. Okay, you'll have to talk to me about that on your own time. So this is a question that has been coming up a lot in my consulting this year. And the question is, what if jobs differ both in their size and also in their value? So specifically, we have jobs of different size. Some are small and some are big, but they also have different value. Maybe the small one is worth many dollars, but this bigger one is worth fewer dollars. Maybe this one is worth only $1, okay? How do you deal with jobs with different values? So to make this formal, what we have here is the dollar signs are indicating the holding cost of a job. This is the dollar cost for every hour that the job is not done. When the job is not done, it's costing me something for every hour. So think of these jobs, they're not necessarily compute jobs. They might be like, should I repair this machine? And repairing this machine, if I don't repair this machine, it's going to cost me $100 for every hour the machine isn't repaired because it's not able to process jobs, okay? But then there's also the size of the job, which is the number of hours of work needed to get the job done. And the question is, if every hour there's some holding cost, okay, some charge that's costing us by not doing jobs, the question is, how do we minimize the time average holding cost? On the one hand, we want to run the jobs that are costing us a lot of money, okay, that have a high holding cost. On the other hand, we want to run jobs that are short because we want to get them done and get their cost out of the way, get their holding cost out of the way. So what should we do? Now, we as queuing theorists know the answer already. The answer is you run the CMU rule. And the CMU rule basically says, create an index for every job, which is the holding cost divided by the remaining size of a job. And always schedule the job's highest index first, okay? So always run the job with a highest index. And that's the answer to the question. But I have to say, when I do this in industry, when I talk about CMU rule in industry, the problems are way more complicated. And I'm actually working on a paper now on some of the complexities that come up in practice. For instance, the holding cost changes over time. The holding cost might depend on other jobs and what other jobs have completed. There's all sorts of interesting problems that come up when you're actually doing this in industry. But even the basic CMU rule is not typically known in industry. And so it's something that I spend a lot of time talking to people about. Okay, I'm going to stop right here. I've given you four different questions. I will skip the fifth and open it up for discussion. Let me see if I can.
Questions for more?
Yeah. So show grid. Okay. So yeah, I am very happy to let other people talk specifically about questions that you get when you go to industry or questions just about my talk or anything. Yes, go ahead. Please.
Hi.
Yep.
Lovely talk. I have a question about the SITA policy where you split the long jobs from the short ones.
Yes.
Do you encounter resistance from people because the pool serving the short jobs is going to be underutilized?
Yeah, so let's go back to that. Let me go to that. So actually, I'm dealing with a project right now with a company on this SITA policy, okay? So right now. So at first, people think that the long pool is going to be underutilized, okay? And I try to explain to them, I talk to them about utilization and what's going to happen. But right now, the company I'm dealing with just simulated it because they wanted to see that it actually worked on their data. And they found that the longs were definitely not underutilized.
But the shorts.
Sorry. Oh, that the shorts are underutilized.
Yeah.
The shorts are not most of the jobs are short.
Okay.
Most of the jobs are short. So what you do is you take a job size distribution and you're trying to basically split to have like equal load and the short queue and the long queue.
Mm-hmm.
Almost all the jobs are short jobs. Okay, 99% of jobs are short jobs. The idea is that these jobs are supposed to be making up half the load.
Okay. Okay.
Half the total load.
Right. Right. And then you configure the two different pool sizes according to what's expected.
You configure and adjust it. And actually, I've written a lot of papers with a guy named Drain Veselo on how to determine cutoffs in these kinds of policies, in these SITA kind of policies. How do you determine cutoffs? So how do you decide how many servers to give to the longs and how many to give to the shorts? If you start splitting it up too much in too many gradations, then you can end up with underutilization problems. But with just two pools of like shorts versus longs, you do not have problems of underutilization. And if you worry that you do, one other thing that I recommend to companies is something I call one-way cycle stealing. So the idea is the shorts, if the longs are being underutilized temporarily because, you know, there are very few long jobs, you can always let the short jobs go and steal from the longs. So you can let the short jobs dive into the longs, okay, and run on the longs. So that's something that you can always do, is let the short jobs run and use the long queue.
But you don't want to do it the other way around because of the risk of bugging.
Definitely not, because then you have your variability problem.
Right.
You definitely don't want to have your variability problem. Yeah, so all of these are solutions for getting around variability. And what's interesting about the SITA thing is, even if you don't know the sizes of the jobs, you can still do something like SITA. It's called tags. But if you read my paper, I probably mention it in there. So you can even do this without knowing the sizes of the jobs. Anything else? Anybody else want to comment on working with industry or things I mean, these are the kinds of things I think we like to teach PhD students because they go out to industry. So it's important for them to know the basics.
What I'm curious is there a difference between educating people in the industry and educating your students in CMU?
So my students at CMU are able to do a lot of math. So when I teach the students at CMU, I teach everything with Laplace transforms and Z transforms. They calculate things like right now on their latest homework, they're calculating the Laplace transform of the FB policy, you know, the FB scheduling policy. And, you know, nobody in industry needs to know any of that. When I talk to people in industry, I don't even talk about calculating performance, not at all. I don't talk about Markov chains. I don't talk about any of it. All I talk about are the basic rules, the basic things that they need to worry about. Utilization, high variability, you know, how to schedule when you don't know the job sizes. This thing about values, different jobs having different values, something that comes up a lot. And there was one more thing that I didn't get to, which is closed versus open systems. I think that's another thing that people are, I know Andre Bondi will probably say this is very important, and it is, okay? Closed and open systems, I didn't get to that question, but it's another thing that comes up a lot with industry. And other than those things, you know, that's enough for people in industry to hear at first. You know, after that, I just listen to them tell me about their problems and try to fit it into one of these things.
Could I comment about the closed systems?
Sure.
Sorry, I see Fernando Paganini that may want to do a question.
I yield.
Before, sorry.
Fernando?
Okay.
Fernando, you are here? Not.